All right. Hi, folks. Welcome back. We got everything squared away for homework, so that'll be the first thing that we get to talk about. Since everybody got it done on time, we get to go over it. So these homeworks are brand new because you guys are the first class I've ever taught for this topic, which means that there will be typos. So I found another one that I've already fixed. So all the typos you've noticed have been fixed. It also may mean that some of the questions are confusing. So it looks like no one got 100% on this, which means that something must not have been sufficiently clear for at least somebody. So I wanted to go over those and make sure that we're all on the same page. So homework 2, everybody I think had no problems filling in the green boxes. In terms of typos, I fixed this. So I had written expected percentage, and this is supposed to be frequency. So the answers are indeed expected frequencies. And then these answers down here are based on whatever numbers you found up here. So most of the time you shouldn't need to refer back to your models or your output because everything that's pertinent that you'd use to make conclusions should already be correct. So which of the following is true about the proportion of students who are 3 years old? So in this data set, it was simulated to be approximately, I think 70%, give or take, 70 to 80. And so most of you should have found that there were more 3-year-olds than expected. So if expected is 0.6. I simulated it so that the students were equally balanced across teachers. And so that would be non-significant, either above or below. The pattern of association between age group and classroom teacher, this is requiring you to look at the difference between the observed frequencies, which are given in the first row of the chi-square table, and the expected frequencies, and to figure out if there are more 4-year-olds with Miss Molly than what should be based on expected frequencies. And so this one would be based on your original data, which is correct. But for all of these, whatever you said, if it's wrong, will be in red, and the correct answer should be given in green. And if it looks like I made a mistake, please let me know, because that is entirely possible. The correlation between age group and teacher was supposed to be, it could be whatever. It's one of those things that varies by data set. So I was looking to see that you could figure out then whether it was significant based on the p-value and then the direction of the correlation. So those things should be up here. And then the last question, Pearson's R as a linear relationship between age group and classroom teacher. So these two variables are each binary. That's the key. Binary variables have a restricted range of correlation to the extent that their means differ from each other and to the extent that their means differ from 0.5. And there is a slide talking about that in lecture 3. Let me pull that up. It should be towards the end if memory serves. Yep. So this idea right here. Pearson's correlation is a restricted range issue when you have binary data. That's why all of these other correlations for binary and ordinal data were invented to try and solve that problem. But that's not this class, that's some other class. Okay. All right, with me so far? Any questions about any of those questions? All right, then we have some more stuff. So I asked you to do some more correlations. So fits thrown and pleases heard. As I said, this is taken out of my life here. Variables that are near and dear to my heart. As I wait for a call from my son's school to see if he got in trouble today, there was a message earlier. I'm like, oh no, please stay at school. I need to do this class.
Does he just want to come home and play with his toys?
I don't know. He got in trouble again yesterday, and but I talked him off the ledge. I talked to him on the phone. Hey, Mommy, are you having problems? No. I'm like, oh, that's not what I heard. But anyway, he does throw a lot of fits and he does say a lot of pleases. So he's somewhat of an anomaly right there. He is the smartest, sweetest little asshole you will ever meet. That's how I describe him. As only the parents of a 4-year-old can understand, right? but I digress. So we did correlations between pleases and fits, as well as, let's see, the other one was fits thrown and age group, pleases heard and age group, and then the last one. So I asked you to run a Pearson's correlation between fits thrown and favorite TV show. Now SAS and Stata were happy to do that, right? It has no problem doing that. So this is a good example of where you can know just enough to be dangerous, right? Because the software won't let you know that you're doing something that doesn't make a lot of sense. Now, why doesn't this make sense? What kind of variable is favorite TV show? Nominal. Yeah, categorical is sort of the broader, you're right. Categorical is a broader category. Special cases are binary, ordinal, where there's an ordering, and nominal. So favorite TV show in this case, number 1 was Paw Patrol. Number 2 was PJ Masks, and number 3 was Peppa Pig. If there's an ordering there, it's debatable. Let's put it that way. We'll call that a nominal variable. So it doesn't make any kind of sense to correlate a quantitative variable with something where the numbers really are just labels. SAS is happy to do that for you, but it doesn't make a lot of sense. So the next unit that we have, we will talk about what you would do instead to try and come up with an association between a quantitative variable and something like this where there's multiple possible categories. It works out to be investigating mean differences in the quantitative variable across these categories and seeing to what extent allowing each group to have a different mean creates a useful expected quantitative outcome. So that's coming.
So there could be a correlation between the type of TV show and the fits, right? Because I know enough 3-year-olds to know when they watch something certain, they act a certain way.
Yes, PJ Masks has Romeo as a bad guy, and he's no longer allowed to watch that because he starts acting like a bad guy.
Okay, so that actually truly happened with PJ Masks with my nephew.
Yes.
His obsession with bad guys and PJ Masks. So that's why okay.
Yes,
so it could be.
But yes, there could be a relationship. The question is, how do you get at it? And if a linear relationship between this variable, where you're treating these numbers as not only numbers but interval, doesn't make sense. So that's what we're going to do next, is figure out what we would have done instead. But yes, there is an association there. It's n of 1 and apparently now n of 2. And 2 points make a line. So don't let your children watch PJ Masks. If you let them watch Peppa Pig, the worst that could happen is they want to jump in muddy puddles. But you must wear your boots to jump in muddy puddles. So, all right. So that was the basis of the last question here. That very last one, which is true about the Pearson R, it is not a valid effect size because it doesn't make sense to have a linear relationship between kinds and numbers. But we can get an effect size, just a different one. Other ones here, most of these are going to be data set specific, but a few of these questions have only one correct answer. So a confidence interval around a sample mean, it's 2 and 3. So if it does not include the hypothesized mean, we reject HO, meaning it is unexpected. If it does include the sample mean, we retain. So we have Z or T provides a significance value for the test as the correct answer for this. Z or T are not effect sizes because what goes into a Z or a T is an effect size and sample size. So it's not a pure measure of effect size. And then I purposefully got these two flipped. Z is for variance unknown, T is for variance known. And then just asking you to interpret what it means to have a correlation among these variables. I think everybody got that pretty well situated. All right, so other questions on this? Okay. Number 66? The answer is you can't have a linear relationship between favorite TV show and fits thrown directly.
But what about the second answer?
The second answer? This answer is not true at all. So the answer to the first one up above, when you have a correlation between two binary variables, it's okay, but it may be limited by the range restriction, meaning that the variables have different means, and so there's less variability than what's possible to the extent that the means are off of 0.5. Number two is a distractor that wouldn't ever be correct in this case. So I just made that up.
So I did have a question. When you have a p-value or for the effect size as 0, how would you describe that?
Less than 0.001.
Okay.
It's never truly 0. It's just 0 to as many decimal places as something printed for you.
Okay.
Yep. So yeah, and because this is correcting to the nearest 100th place, so if it's past that, it just enters as 0. All right. Other questions? So much to your dismay, yeah, I heard that. Homework 3 is ready. You had one shining moment where you were caught up, right? And I took it away. But you know what? Now it's my turn to have the shining moment because you're all working on the homework and I don't have to make a new one. So we'll just share. It is going to be due a week from tomorrow. So it was supposed to be due on Monday, but because I wasn't sure how long it would take to get through the next topic, I wanted to make sure we had one more class. That way you have a full week to work on it. And so it is through the 23rd. However, I didn't put anything on it that we won't have finished by today. I'm quite certain. So you can get started on it anytime you'd like. And we'll have a quiz that will be due before the next class that we'll go over on Tuesday. Reminder, we have no class this Thursday. So homework 3 features the same data set as homework 2, but now you're going to run models. And no TV shows yet. We'll get to that. That'll be the next homework. All right. Exciting, huh? Yeah. So let's see. Where do we want to pick up? Where would I like to pick up? Let's close out of lecture 3. We'll close out of this. And let's go back to lecture 4. That one. So we're reviewing the idea of models, right? So general linear models predicting quantitative outcomes from any kind of predictor. So far, we have looked at just including one quantitative predictor. And what would other people call that? Starts with an R. This is a vocabulary quiz. Yeah, what is it called when you have a general linear model with a single quantitative predictor?
Residual.
Close. The model will have residuals, but it gets a special name.
Regression?
Yeah, that's a regression. Yeah, a simple linear regression. Simple meaning only one predictor. Linear distinguishing this regression versus other kinds, which come back next semester if you want to know what other kinds there are. Those are generalized models. And what do we do to make sure that our predictor has a meaningful 0 value? Center. What is centering?
Making sure that the 0 has a meaningful value.
That is the goal of centering. What do we do? And feel free to read from the screen. What is the mathematical operation? Rescale it. More specific. Such as?
Use a linear.
Subtract or add a constant. It's usually subtract because most variables are positive values. If you have a variable that starts at 0 as a meaningful score, that's fine to leave it alone. So, like number of fits thrown. It's theoretically possible for there to be a day with no fits thrown. I have yet to see one, but it's possible. So in your next homework, I will be asking you to enter centered predictors. So you will be centering pleases heard at 7, I think, and fits thrown at 5. And that just means create a new variable by subtracting those constants. We do that so that the intercept is a meaningful value. The intercept is always the expected y outcome when all of your predictors are 0. So this slide is illustrating the difference in what happens if you put in a centered predictor of education versus an uncentered predictor. In the uncentered predictor, the intercept refers to the expected income for someone who's never been to school, which, while theoretically possible, not very useful as a reference point. Our centered model switches the intercept to be someone who graduated high school, and now we can talk about what is predicted to happen to their income for each additional year above high school or year below high school. So, spoiler alert, look at this picture for just a second. Do you think a straight line is the best choice to go through these dots? No, it kind of looks like at some point, like if you don't have a high school degree, you're all sort of, it's like flat, and then there's kind of a jump, and then maybe there's some indication of a positive effect of education. That's what we're going to do in the next unit, is figure out how to fit nonlinear effects of quantitative predictors. So having multiple slopes to work together to describe the net effect of a variable. So stay tuned for that. Yeah, I know, right? It's exciting. And you said residual, so let's do this one. What's a residual?
Stuff not explained by your model. Stuff
Stuff that's not explained by your model. What's the mathematical definition of it? Because you're right, but let's go one step further. How do I get a residual for each person?
Observed minus predicted.
Mm-hmm. What you had minus what is predicted for you. So in this case, if I have the empty model, they actually got 155. It was predicted to be 40, so we're off by 115. So that no matter what the model has, the definition of a residual is always the difference between the outcome you really have and the one that is predicted for you by the model fixed effects multiplying the predictors. That is always what a residual means. In the empty model, if we have no predictors, then this residual is giving you, if you take the variance of these residuals across everybody, that's all the variance there is in the variable. Once you add predictors, if the predictor matters, if its slope is significant, you should see this residual variance go down. It will never go up. More question. It's either down significantly or down non-significantly. Because this is all the unknowns to start with, 1980. There's no way you can make it worse, at least in this class. Stay tuned for the afternoon class for when that can actually happen, but that's neither here nor there. All right, so these things will show up on your output. Your third homework, you will ask you to locate these. The estimate, best guess for what a slope is or an intercept is. It's standard error, an index of, by the way, we looked this up at home, it's imprecision. It wasn't M. It's like, I am not crazy. I got that one. Imprecision. If you take the estimate, divide by the standard error, that gives you your test statistic. So the estimate is how far off your slope is from 0, right? So it's kind of like an effect size, but it's in an unstandardized metric. Standard error, what goes into standard error? 3 things. Residual variance, variance left over in y, sample size, and the variance of the predictor to make sure that the scale works. So it's the same idea of the t-value is both a combination of your effect size and your sample size. So we would want to compute or ask for a standardized version of this fixed slope to try and talk about effect size in absence of sample size. And that, let's see, that formula showed up a little earlier, I think. There it is. Standardized. So you can compute this yourself, but you know what I would do instead? Get the software to do it for you. So in Stata, it's regress, comma, and then the word beta, and that adds standardized effect sizes. In SAS, it's either proc GM select or proc reg. We'll give them to you. So we have that in our example as well.
GM selector, what was the other one?
Proc reg, R-E-G. Sorry, that's my northern accent coming out. Reg, bag. Like if you go through Minneapolis, they're like, make sure you put your pink tag on your bag. I slip into that occasionally, even though I'm not really northern. This process, by the way, of estimate over standard error becomes a t-value or a z-value. We call this a univariate Wald test. This is the idea that we are testing one slope. We will, starting, maybe later today, hopefully later today, we'll be able to test more than one slope at a time. Can you guess what it's going to be called then?
Multivariate.
A multivariate, yeah. You already know these words. They're just coming back in a different context. Yeah. In terms of predicted outcomes, the standard error for a predicted outcome is going to be smallest near the mean of the predictor. It gets a little bigger as you head out. And that, do you want to see the code that goes along with that?
Yes.
Would that help? Since you're going to have to like use it and do stuff, you know.
What slide is it?
We are on slide 19. Yeah, we got this far, and I don't think we've gotten into the categorical predictors yet, if memory serves. But let's look at example 4. So all of the models and the results that I put in the slides, this is how I got them. So we're working with the same subsample of the GSS data with 100 people so that we can make pictures more easily. Here is an example of how I would center a predictor. So in SAS, it's new variable equals old variable and mathematical operations on it. So EDUC was a variable that's already in the data set. I am subtracting 12 from it to make a new variable that I have named education 12. You can name it whatever you want. I tend to stick the centering constant in the name somewhere so that I know what the 0 point means. That's just a habit that I have. In Stata, it looks remarkably similar. No semicolon, and throw the word gen in front of it. So you'll need to be able to do that. I have no doubt that you will be successful. Descriptive statistics, you guys know how to do that very well by now. Here's some pictures. Correlation. So when you only have one quantitative predictor in the model, the standardized effect for that fixed slope is the Pearson correlation. So this correlation between education and income of 0.45, you're going to see that again show up in the standardized solution. That is only true when you only have one predictor, though. So you're going to have to do this empty model. What does empty mean again? No predictors, meaning that all the prediction is coming from this fixed intercept right here. Is this a constant or a variable? Constant. And in Stata, it is called the constant, by the way. It's underscore and then CONS, like constant. That's what they call it. I hate that because all slopes are constants, but that's just what they call it. I call it intercept. Because if you don't know anything else about a person, your best guess for their outcome is, ding, E is how far off each observation is from the mean. That's how we get variance. All right, so there are two parameters, two things to be found by the model. One of them is that mean, beta 0. That is right here. Intercept. In Stata, this will be underscore and the word constant. Yep. And so the labels on these directly map what we just talked about, the estimate, standard error. So this is the standard error of the intercept, which you guys already know is the standard error of the mean, right? That's how far off this sample mean is on average from the population mean. Estimate divided by standard error gives you T. T for denominator degrees of freedom of, looks like 95 here because we have 96 people all together. We spent 1 to get the mean. Gives you a p-value of less than 0.0001. Where is my residual variance? There's a lot of other numbers up here. I'll give you a hint. I bolded it, trying to help.
1980.
Yep, that's the 1980, yeah. So we will get into where this table comes from next. But for now, just find it here. Mean square error is what it's called. I don't like the term error because it makes me think I screwed something up, but mean square residual is what I will call it. Okay. With me so far? All right. Non-empty model. Putting in education uncentered. So this is a model that is perfectly valid but weird. This is the one that provides a fixed intercept of minus $52,000, which can't happen. That's what happens when you extrapolate the line, the regression line, past all the data to get to education equals 0. The slope for education, though, is just fine. So the slope, when you have a linear slope like this, does not care how that predictor is centered.
Which one's the slope?
That one. It's this case, it is the slope of education specifically. So this is beta 1 in my equation here. Is beta 1 a constant or a variable? Beta 1. It's a constant because everybody gets the same slope that multiplies their x variable. So this is why I don't like the term the constant is beta 0, because beta 0 is a constant and so is beta 1. So you can always tell in an equation the things that have i's are variables. The things that don't are constants. Another term that you will hear, these are fixed effects specifically. This is an intercept and this is a slope. Later in statistics, there are other kinds. Random effects, in fact. But that's the next class. Variance left over, it went from 1980 down to 1594. And I know that that is a significant reduction because my slope is what would have had done it. The only way the variance can go down is because education explained some of it. Why is it that some people make more money? Because they have higher education. And there's my regression line. So then I fix my model by centering education. So note that I am putting in the education 12 version of the predictor instead. Otherwise, everything is as it was, as it were. In terms of the solution, the only thing that's different is right here. The fixed intercept is no longer minus $52,000. Now it is $27,000 because that is the expected income for a high school graduate in the sample.
This is the center.
And the slope is still 6.6 because it's a line with a constant slope. And there's my picture of residuals and the regression line.
Can I ask a question very quickly?
Sure.
When we're talking about this slope, that is not a regression. No, you said regression. That is not an R.
It is an unstandardized R.
So I couldn't say that's like a positive correlation with the slope?
Yes, you could say that because the next thing we want to do is get a standardized estimate for this. This 6.6 only has meaning in terms of the scale of the x variable and the scale of the y variable. Like looking at this, you wouldn't know if that's good or not.
Okay.
So we can standardize y and x, and then this becomes a correlation. And
this
then
correlation, the number we can make meaning of it. It means something.
Immediately.
This 6.6 means nothing to us really, like outside of this.
Exactly. You'd have to see the rest of this to know that 6 is good or bad, or not noteworthy. But yep. So in the case where you only have one predictor, the standardized slope, so let's go ahead and grab that, right here, is the Pearson correlation. So this is where in Stata, you can get all of it in one shot. In SAS, you have to run something different to get the standardized effects. So one way to do it is this one, GM select. I found out the hard way this morning that apparently you need to add one more command, so I updated the handout. If you printed this before, make sure you have this on there. That's a new option, selection equals none. By default, it tries to go through and figure out which predictors should be in your model, and I don't want it to do that for me. So this output has a new column in the middle, standardized estimate. So what we were looking at before is what's known as unstandardized. It's the intercept and slope in the original metric of x and y. Standardized means we standardize x and y to be in a z-score metric where each has a mean of 0 and a standard deviation of 1, variance of 1. So the intercept standardized is always 0. Slope standardized becomes some kind of correlation. It's the Pearson correlation if you only have one predictor. It will be related to something else called a semi-partial correlation if you have more than one, but we haven't got there yet. Okay. How are we doing? Good? Okay. So yeah, this is not telling us anything we didn't already know just by running a correlation between these two variables. And what do you think would happen if we flipped it and I had education as the outcome and income as the predictor?
The slope would flip.
Yeah, so these unstandardized would flip, but standardized would be the same. Yeah, they won't invert, but they'll adjust to take care of the difference in scale. It's units of y per units of x. All right. Questions on any of that? Okay, so binary predictor, let's do that. So categorical predictors in general, we can start with binary as the easiest case and then work from there. So I'm starting on slide 20. So in general, if you have a categorical predictor that we're calling it, saying we have C categories. So if you have like a 3 category variable, you need that many fixed effects in your model. So if I have a binary predictor, that translates to 1 fixed intercept and 1 fixed slope. And the slope will carry the difference between the people who got a 0 and the people who got a 1 in the outcome. If I had 3 categories, then I would need 1 fixed intercept and 2 slopes. So that one we'll do next. So let's say now that x is binary. So before we had education, if x is a binary variable instead, it is no longer a regression. It's a 2-sample t-test, even though we use t all the time. It's a bad name. But so don't worry about that. But let's say we're looking at income and marital status. I hypothesize that people who are married have more income because there's 2 of them making it usually, not just 1. Or at least they get to share expenses, even if there's only 1. So in this case, to know what the intercept means, I have to know how this variable is coded, what values are being used. The easiest thing to do for your sanity is to have it always be 0 is somebody and 1 is somebody else. I don't care who's who, but make one of them 0. Because that way your intercept is the expected outcome for the 0 group. Your slope is the difference in the outcome between the 0 group to get to the 1 group. What if I had a binary variable that was coded 1 and 2? Could I do this? Wrong, weird, or both, or neither? Weird, not wrong. So I would put in my categorical variable of a 1 and a 2 here, and my beta 0 would be the expected value for a group coded 0. I don't have that group, it's not going to stop it from making that intercept. The slope for married, so long as the groups differ by 1, will still be the group difference. If you picked something like 1 and 3, then you'd have to take the slope and cut it in half. So just make it 0 and 1. It'll make your life easiest. So then the residual, same definition as before. It's always how far off your real outcome one is from the one that's predicted for you. But now we can think of this as remaining income variation within each group, within the married people and within the not married people. And this always keeps moving. I fight with PowerPoint so often. It wants to like move my things over to be centered, and I don't know why. But I am going to win. There. Stop that. There. So here's a scatter plot to show this relationship in the GSS data, the subset that I use. Now this looks kind of weird. Well, because there's only 2 possible values for married. Not married, which is 0. So here's the income spread amongst the not married people. And married, which is 1. And here's the income spread amongst the married people. There's some really rich people at the top here, but most of the people are right in this area. So the slope, in theory, could talk about what it's like to be 0.2 married and 0.4 married and 0.6 married, which is weird, but this translates to just a straight mean difference. What is the predicted mean for the 0 group right here versus the predicted mean for the 1 group? So it's a means comparison is what it boils down to. So if I estimated a Pearson correlation between these 2 variables, then in this case it's 0.3, which is significantly positive. So married people are slightly more likely to have higher incomes. The model tells me what the predicted outcome would be for either of my 2 groups. One of them is given directly as beta 0 for the 0 group. The other one is implied as a linear combination. So if we do the math here, in fitting this model to these data, it came up that 25.5 was my fixed intercept. That's always going to be for my 0 group. So I got to think back to my coding. Who is that? That's the not married people. So not married people on average have $25.5 thousand. To get the predicted value for any other group, we take the slope, so the estimate for beta 1 is 26, and multiply it by the value of the X predictor that it's the slope for. So if what I'm predicting is for the unmarried group, I put in a 0 here, because that's married equals 0. That's who we're predicting it for. That drops. And that's why their predicted outcome is just the intercept. The same thing happens for your reference point for a continuous quantitative variable, because that's when you put in a 0 and the effect of the slope is removed. The other group, though, it's 25.5, the intercept, what it is for 0, plus how it differs if you're in group 1. It differs by 26. So the implied group 1 mean works out to be 52. Now you can do this math yourself, but what is harder to do yourself is to get a standard error around this number. So one of the other things that I'm going to teach you, in addition to running the model to get these fixed effects, is how to ask the program to give you a linear combination of fixed effects, such as is needed to predict the means for the other groups who aren't coded 0. So E then is the difference between what is actually there and what is predicted for your group. So in the non-married group, E would be their actual income minus 25. In the married group, it's their actual income minus 52. So do you remember this thing, Y with the pointy thing? What do we call that?
Y hat.
Y hats. What does it mean? Model predicted outcome. So when we talk about Y hat, there's no E, because we're saying, okay, given your pattern of X's, what's your Y going to be? E then steps up to differentiate your predicted value from the one you actually got. Okay, so let's see it. Last model. Here's how I got those numbers. And yes, you get to practice doing this for your homework 3 as well. So married is a variable that was already in my data set. It's coded conveniently as 0 versus 1. So if you have a variable that's coded some other way, you'd want to fix it so that somebody is the 0 and somebody is the 1. So y equals married. This much you've seen before. This is something new. The analog in stata regress y, and then the next variable is an x, comma delineates the end of that line, and lincom does the same thing as estimate. So this and this are equivalent. So this skill, by the way, in my advanced classes, I spend a good month, the first month, teaching this because no one has seen this before. So you guys are going to be like the inaugural class that goes and kicks your upperclassmen like acids on this. Because you're going to be like, I got lincom, I got estimates. No, for real, Joe. This is such a helpful skill. The idea here is that the model only is going to give us estimates of the model parameters, the things that we are directly asking for. So we don't have to ask for beta 0. The fixed intercept is always given to us. We'd have to shut it off, in fact, if we don't want it for some reason. By putting in one predictor, I am adding a beta 1. Can you guess what would happen if I needed another predictor? Let's stick it in here too, and then I'd be adding a beta 2.
Would you just put it right next to married?
Yep.
With space?
Yep.
Asterisk, just straight
Just space, just space. Asterisk means interaction.
Oh, well,
That's
we don't
coming.
want to interact.
Not yet. Not until like November.
Oh, can't wait.
I know, right? So these are the two things that are going to come out. We've got, so let's start with those. Right here. Intercept. My estimate is 25. That's my outcome for the 0 group. 26 is the slope for married, which when married is a binary variable, translates into just a mean difference. So relative to my intercept reference group non-married people, married people have a higher income by $26,000. So the 0 group is the reference. It's the you are here sign of the data. The fixed intercept gives me this expected outcome for that reference group, the group coded 0, which is unmarried people right now. Relative to 0 group unmarried people, 1 group married people have an income that is 26 higher, 26,000.
Higher?
Higher, because it's positive.
So it's not the difference between the two?
It's not the difference between the two. It's the two of these added together get to what the income is actually predicted to be for the 1 group. Question?
I'm just calculating. Trying to see it.
Trying to see it?
Yeah, no, I got it now.
Okay, I'll show it to you. So this is my model equation to predict income if I'm in group 0. Intercept plus fixed slope for married times the value of the variable for married equals intercept in this case because that's gone.
Yeah.
Predicted income for the 1 group,
Oh, okay, I see.
intercept plus difference times 1, so it's like the 1 turns the difference on,
Okay.
works out to be 52. Now where did this 52 come from? Well, I added up 25 and 26, right? But in addition to wanting to know what the predicted mean would be for the 1 group, I also want their standard error, and I might also want a confidence interval. Those things can be done by hand, but I would not want to do that.
Yeah, I was just, so like the income for the married, or
Mhm.
like right there. Not right below you. No, you're good. Back, go back. Yeah, I was just trying to see where it says estimate 52.24. That's what I was trying to see. I was like, oh, I was like lining it up. I was like, okay, I get it now. So.
Yeah. So 25 and some change plus 26 and some change is this number.
Yeah, that's what I noticed.
So this is the skill that your guys are you're gonna rule because you have this skill. So what I'm asking it to do is do a linear combination of model fixed effects to make something new.
What fixed effects?
The fixed intercept and the fixed slope.
Oh, you said it was a linear combination.
A linear combination.
Of blank fixed effects.
Of linear combination of fixed effects. That's enough. That's what these estimate and lincom statements do. Now the one for Stata looks a lot more like the equation implies. So in Stata, there's this const, that's beta 0. So if I want to predict the income for somebody who's married, I need 1 beta 0 plus, when I put married here, what I'm actually referring to is its fixed effect in the model, its slope. So it's going to go figure out what beta 1 is and then use it to make another predicted outcome. And since I'm putting in a slope, it also wants to know what is the value of the predictor that's supposed to interact with the slope. It's the 1 group. And so I put in 1. So the 1s aren't strictly necessary, but I put them in here for symmetry with this. So this beta 0 plus beta 1 times 1, that is a linear combination of model fixed effects that this is then going to estimate for me and get me a standard error, a t-value, a p-value, etc. So that's where that line came from. In SAS, it's similar, but without the explicit math. So it's the word intercept. The thing that is to multiply it is a value placed by itself. It's implicitly plus because all of these values are positive. Married refers to the slope, and 1 is the value of the predictor that I want to multiply that slope. So we're going to see a lot more of these. This is your very first one.
I'm sorry, I looked at the also there. So why do you have a 1 behind the intercept and 1 behind the?
The 1 behind the intercept is to make it look parallel to this. What the word intercept refers to beta 0.
Yes, but why have a 1 behind it?
Because you need one of them to contribute to this prediction.
Okay. Maybe also.
The 1 after married serves a different purpose. It's filling in the value for the group that you want the prediction for.
So it's the 1 behind the married is for the married and the unmarried we want the married.
Yes. Yes.
You can also put a 0 there, right?
Absolutely. So if I wanted to do, we'll just pretend we're doing this here. Income for unmarried. I keep the intercept. I need a beta 0, but I would substitute in a 0 there. And now why didn't I write this? Anytime that you see one of these things where there's only one number filled in, it's already in your model. So this is using the same logic of a linear combination of fixed effects to give me what is functionally just beta 0. So I don't have to write it. It's redundant with what's already in the model. It's not a linear combination. It's just beta 0 again. So in total, for this binary variable, there's 3 things that we would want to know and report. What's the mean for the outcome for group 0? What's the mean for the outcome for group 1? And are those means significantly different? Any model will only give you 2 out of those 3. because the third is redundant. It can be found from the first two. So this model is phrased to give me the mean for the 0 group and how different the mean for the 1 group is from the mean for the 0 group. By putting those together, I get to what the mean for the 1 group is actually predicted to be. So there's a homework question asking about what this slope means in the context of binary data. Our slope is positive. That means the 1 group is higher than the 0 group. If the 1 group were lower than the 0 group, this slope would be negative instead.
Is
So-
that being the estimate will be minus?
Mm-hmm. Yeah, so if married people made less money than the 1, then being a 1 would cause your score to come down relative to being a 0.
Well, why don't we do the married one, the estimate is smaller instead of.
So this intercept is the income for the 0 group, who is unmarried. This is not the mean for the married group. This is the mean difference for the married group. It's a slope. It's always phrased as a difference. The mean for the 0 group plus the mean difference for the 1 group gets us to the mean for the 1 group, which is the 52. Does that help? Yeah, this, by the way, this is a very common error to look at this and think that's the mean for the married group. It's not. It's a difference.
So did you just say that the intercept is also the mean for the married group?
The mean for the unmarried group is the intercept because that's the group that's coded 0.
Okay.
So let's think about it. What if I switched it? What if I changed my variable to be the effect of unmarried? Can I do that? So 0 means that you're married and 1 means you're unmarried. How would my numbers rearrange themselves? Well, now, if married is the 0, 52 is my new intercept. And if my slope is the effect of being unmarried, beep. And now the linear combination that is implied, but not given directly, would be the mean for the 1 group, which would be 25. So you only get 2 pieces of information. You got to get the third by asking, always. There are different ways to code this so that the model parameters are the means for each group directly. I thought about showing that to you, but then I thought, let's not be extra confusing when you're just learning this stuff for the first time. So just know that all models are always in the context of specifically what you put in it. If you have a fixed intercept, functionally speaking, it's multiplying a variable that is a column of 1s, meaning the fixed intercept applies to everybody. Then we talk about what is the deviation off of that for the other predictors. So the slopes then are always differences. It's the difference in the outcome per unit x. In this case, per unit is just the group 0 versus 1. And I didn't ask for a standardized coefficient for this one. It would be the correlation between the two, which is 0.3. For binary variables, an R doesn't make as much sense usually as another letter, which you're going to meet soon, which is D, which is a standardized mean difference. So that's what I would end up doing instead. And because I like you guys, and I want you to like me, here are some words. You may not like me as much after homework 3 is over, but I can live with that because then you'll maybe hopefully have learned this stuff for real and you can feel really good about that instead of really afraid Right, Cole? Right, he's like, I haven't. Yeah. Okay. Questions so far? We're almost done, but not quite. Okay. So one of the things that you have to keep in the back of your head while you're doing these things, what choosing the GLM means. Slide 23. We just have a few more left. So a quick story. When I was a postdoc, hang on, I'm dropping my quote here, at Penn State, I volunteered to be a pretend client in a statistical consulting class. So there was a master's program in applied statistics, and that's where people went to go be consultants. And I was supposed to come in with a problem, and they were supposed to practice asking questions of me to figure out what I needed to do. And they said, okay, what's your outcome? What's your outcome variable? I said, it's response time. I came with the story in my head. And the next question, I kid you not, does it meet the assumptions of the analysis? I said, if I even knew what that question was asking me, let alone the answer, would I be here? So at some point, some reviewer or someone else is going to ask you about assumptions. Now, I'm going to tell them to you, but I'm going to pitch it differently than what other people might. Whenever you choose a model, you are choosing how that model works. That's like if you go to Wendy's and you're like, I'd like a double with cheese. Well, I am assuming that I am going to get 2 hamburger patties, a slice of cheese, and no bacon, right? Like that's what I ordered. So when you order the GLM, you are also ordering certain choices that may or may not be appropriate for a given data set. The conventional wisdom is to try and fix your data in those cases to fit the model. You will hear me say the opposite. You choose a new model that would better suit your data. So this is the first set of models that you guys are learning. There's way lots others out there, but they all have this one as a core, and they build on it to incorporate other things. So I just wanted to give you a sense of what else is out there, as well as a sense of what you are doing when you choose a GLM, a regression, an ANOVA, a t-test, etc. So we are choosing the normal distribution to describe our residuals. That's what we are choosing. If that is not plausible, we need to choose something else. But it's important to distinguish the difference between a model outcome and a model residual. Outcome is what you get as a residual from the empty model. It's the original shape. What we are saying is that the part that's left, the E residuals that differentiate how far off your Y still is after you're done predicting it, that's what's supposed to be normal in these models. So the term that you will hear for this is conditional normality. It's not that Y is normal, it's conditionally normal, meaning after we predict it with all the X's, what's left is normal. The residuals are normal. And so you will see it written this way, Y sub I, so that's my original variable, squiggle, do you remember what that means? Tilde, what does it mean though in this context? I mean that sometimes in other contexts. Yes, I do that. Yeah, this means ish a lot when I write things, but that's not what it means today.
Distributed?
Yes, distributed. Yes, it's been a few weeks since we saw that. So what we're saying is that Y is distributed normally. So N sometimes is sample size, sometimes it's normal. I'm sorry, there's only so many letters that we can choose from. And the parameters of that normal distribution, remember what the two are? What are the two things we need to know to describe a quantitative variable that's supposed to be normal? Mean and variance, or mean and standard deviation, because standard deviation squared is variance, one of the two. So what we're saying here in parentheses is that the mean of Y is Y hat. It's the Y given from your predictors. So it's not one mean, it's like a mean for like everybody, because anybody who has the same X gets the same Y. And the residual then, the variance is the residual variance. So this is the idea of conditional normality. By not having the mean here, by having a conditional mean, a mean that is predicted by the X's, that's conditional. That's what's supposed to be normal.
Can you see?
You said the O2, that's like the, sorry, that's not an O, but that's the conditional variance for everybody?
The term is residual variance, but I think you could say conditional variance. Variance left over is the concept, unexplained. So in this model, all we have so far is education. So this sigma squared E, the blue thing, that is the variance of the E's, the difference between the predicted income from education and the one you actually got. So it's all the reasons why some people still get more money irrespective of their income. I almost said irregardless, but I stopped myself just in time. Because I know that's not a word, but sometimes you want to say regardless and you want to make it even more emphatic, like irregardless. That's where I was going, irregardless of education. So this was our original outcome. And we all agreed before that this ain't normal, right? It's, even if these people weren't out here, it's still kind of like wonky. This is the residuals after education. Now, they're not perfectly normal, clearly, but they're more improved. So part of the reason for this skewness has been explained. The reason why some people have these hella huge incomes is because of their education. So that's one thing. So when you have a quantitative variable that doesn't have like obvious boundaries, odds are pretty good that something might look normal. But what if we tried to predict something like a binary variable? Like it's like 0 or 1, right? Can the residuals from 0 or 1 ever have some sort of shape to them besides just two piles? No. So this would not be a good choice. That's like ordering the double cheeseburger and saying, oh, can you make it vegetarian? It's like, no, it's a cheeseburger, right? This is a linear regression, the idea that we're predicting something where a linear model should have some sort of spread in what's left over. Now, what is it if you want to predict a binary outcome? Generalized linear model. That's next semester. Come on back. The other thing, another come on back cell for my other courses, is that the general linear model is for residuals that are independent, not related. So the opposite of independent in statistics is dependent, which means correlated. So like if I'm talking to one of my colleagues, Ariel, and we're talking about how our kids both love Paw Patrol, you'd be like, wow, that's a huge coincidence until you think that they're both 4-year-old boys. Like once you condition on the fact that you have this, this, and this in common, then you're conditionally independent. So people don't have to be independent, but they should be after you put in all the predictors that would make them related to each other. If that is not true, so for instance, if you're in an educational setting and you're collecting data from multiple students from the same teacher and multiple teachers who work at the same school, even after you put in your predictors, the students from the same classroom might be more alike in certain outcomes. Teachers from the same school might be more alike than teachers from different schools. You cannot use a general linear model for that. You need to come to my next classes. Those are called multi-level models or mixed effects models. And the idea is that rather than having just one E for variance left over, you have as many E's as you have different levels of sampling. So like you'd have an E for teacher differences, an E for student differences, an E for school differences, and that kind of thing. Those models then take the general linear models as starting point, and they add more types of E's, broadly construed. Also happens if you have longitudinal data. If some of your outcomes come from the same person, they're more likely to be more related than outcomes that come from different people. So general linear model, not appropriate for that as well. The last one, these are some new vocabulary words. General linear models assume or are based on the idea of homoscedasticity. I can't even make this up. In English, constant variance. Our model only has one number for the residual variance in it. That implicitly assumes constant amounts of variance across all of our people. So I like this picture, so I steal pictures from Wikipedia that I like rather than making them, because I figure why reinvent the wheel. But here's the sources for that. So the idea here is that for every point on a regression line, there should be a spread of e's around it, and the spread of e's should be like relatively equal around the line. The line should not work better for some people than others. So here's some other pictures over here. I like this one. Good. So this is relatively constant amount of variance around the line. This is not good. Because here, the error of prediction, how far off these e's are from the line, increases as the variable increases. Now that's not necessarily a problem. That may be life. But if that is what your data look like, you need to add extra e's to the model. You need to allow the e to increase along with x. Those are called heterogeneous variance models, or location scale models, or come back in a few semesters for those, but just to put it out there, you're not stuck with a broken model if this is what it really looks like. And in fact, in our data, with respect to education, that's kind of what it looks like. The model does a less good job predicting income as education appears to increase. So that just says that both the mean and potentially the variance left over increase as a function of education. Now where that causes problems though is if your model assumes constant variance, then the standard errors are going to be too small in some parts, actually too small in some parts and too big in others, because constant variance is an average of what you get. So you may need to order something different at Wendy's. It's like a side salad. I don't know. I mean, there's not a lot of choices, but the plot on the right here, with the exception of a few outliers, this would be an example of homogeneous variance within groups. So the variability in income after controlling for whether or not you're married appears to be relatively constant. And so this model seems fairly appropriate for this. Okay. So putting it all together, we've entered the world of linear models, predictive linear models. The ones that we're sticking with this semester are the general ones, using a conditional normal distribution. If that's not going to work, generalized models for other kinds of distributions would be a better choice. So far we've got to the empty model and putting in one predictor at a time. So the definition of these things is always the same. The context of how you interpret it is variable specific. So if we write this generically, y sub I equals beta 0 plus beta x times x sub I minus c plus e sub I. Like blah, blah, what? Well, beta 0 is always the expected outcome when x is 0. So it's either where x is 0 as you've centered it, or the 0 group in your binary predictor. Beta 1 is always the slope that goes along with the predictor. It is the expected change in the outcome per unit difference in the predictor. So if it's a quantitative predictor, it literally is per unit, like along the line. If it's a binary predictor, per unit just means going from the 0 group to the 1 group. E is always how far off your real outcome is from the one the model predicts for you. So model predicts for you depends on how many betas are in here and what predictors they multiply. E is always what's left. And in ordering these models, we are saying that the E's are supposed to be normally distributed, they are supposed to be independent across persons, and they're supposed to have constant variance, homoscedasticity, across the predictors. If not, don't go to Wendy's, go somewhere else. Go to Runza. Does any of you know what Runza is? No, see, this is a Nebraska thing. You can't hit a rock without finding a Runza. And they don't exist anywhere else, and it makes me very sad because their hamburgers are great. And their onion rings too. Okay. See? How we doing? So what's next? The thing that I thought we might get to but didn't end up getting to, which I'll be working on the road. How do we put in a 3-category variable or a 4-category variable? How do we make a slope through a quantitative variable that's not linear? That's the next thing.
And this new lecture will not be on homework 3?
Correct.
So,
Yes, so you know everything you need to know to do homework 3 right now. I will let you know when your next quiz is ready, and that should be coming later today. So no class Thursday. See you next week.
So, so that one's not ready yet.
It's not ready yet because I wanted to see how far we got. So I will put it up later this afternoon, and we'll go over that next Tuesday. Homework 3 is ready.
and Lisa, I lied. There is not a line between your son and Ronan.
No?
It was Jake and the Neverland Pirates that he wasn't
Oh.
allowed to watch anymore.
I don't